The next topic that we are going to consider in our look at thermochemistry is energy and how we can calculate energy using a couple of different tools in the lab. Now, to do this, we have to bring in a couple of terms, and I really don't want you to get hung up on this. Actually, I'm going to tell you to scratch out a little bit of this. But work, we said, was caused when we're pushing or pulling against an external pressure. And to calculate work, we look at a lot of times that work is equal to a negative pressure times the change in volume. So both of these situations that we're going to use to measure the heat energy exchange is going to get rid of the work aspect and relate heat to energy. So let me kind of show you what's going on here. Oh, I didn't show you that, sorry. So with this, all you have to know is that when we get into calorimetry or calculating energy, calorie measure is what calorimetry stands for, that we don't really have to keep work into play. What I'm even going to have you do in your notes is mark out these work calculations because really we don't need them. What I need to get to you is the idea that the energy of the system for our purposes is going to equal the heat, okay? So again, we're dealing with the energy of the system is going to equal the energy of the surroundings, but with opposite signs. For instance, the heat that the system gives off is going to be the heat that the surroundings take in and vice versa. And the tool we're going to use to do this is called a bomb calorimeter. Now that sounds pretty exciting, but I hate to burst your bubble. It's really not all that exciting. It's a device that looks sort of like this. And you put your sample, you grind up your sample in here to a really fine powder, and then you combust it. Well, when you combust that sample, it's going to give off heat. And you can measure the heat that that gives off. Now, there are some things you have to take into consideration, okay? One of which is the heat capacity of the calorimeter, or how much that calorimeter absorbs. So that's going to change kind of your value. So that's something that has to be figured in, and they have to give you that value. Now, remember, specific heat capacity is joules per gram Celsius. Notice with this, the C of the calorimeter, they're just talking about the whole calorimeter, not per gram, not per anything like that. And notice it's a larger value. It's kilojoules. So just to make sure, just a moment of review, there are 1,000 joules in 1 kilojoule, okay? So we're looking at a much larger heat value here. So let's take a look at some problems that utilize a bomb calorimeter. So we've got 1.0 grams of sugar, and we're going to combust it in the bomb calorimeter. The temperature is going to go up. We would expect that. And we want to find the delta E for the reaction for the combustion of sucrose. And check this out, the units they want are kilojoules per mole of sucrose. Do we have a mole of sucrose? No. Okay, remember we can find that with the molar mass using our periodic table, and you know right away that's going to be a big old number, not this. So we'll deal with that in just a second. The heat capacity of the bomb calorimeter, they tell us, is 4.90 kilojoules per degree Celsius. Okay, so let's see. Let's see how we could calculate and do this problem. Okay. Again, I'm going to give you the formulas here. we'll look at the back cover of the book. If this one, for by chance, isn't on the back cover of the book, I'll give it to you. The Q of the calorimeter is equal to the specific heat of the calorimeter times its change in temperature. In other words, the heat that the calorimeter takes in is going to equal this value. So that's going to be 4.90 kilojoules Celsius times our T final minus our T initial. Well, that's 28.33 degrees C minus 24.92 degrees C. So the Q of the calorimeter is equal to 16.7 kilojoules. That calorimeter heated up, absorbed that much heat. Well, the Q of the calorimeter, the heat that the calorimeter takes in, has to be equal to the heat that the reaction gave off. We just combusted sugar, okay? So we have negative 16.7 kilojoules of heat from the 1.10 grams of sucrose, or C12H22O11. That's what produced this heat. Okay, well, that would be kilojoules if we divided it by this per gram. So we're going to have to change it from kilojoules with grams to moles. So the first thing, I'm going to keep this value, but I'm going to change this to moles. Okay, so if I do that, I've got 1.010 grams C12H22O11. There's 342.3 grams C12H22O11 and 1 mole of, I think you get the idea, and we get 0.00295 moles. Okay, well, I'm out of room, so I'm going to go this way. If that's the case, we're going to take our negative 16.7 kilojoules, divide that by our 0.00295 moles that we just got, and that's going to tell us that we got a negative 5.66 times 10 to the third kilojoules per mole. Now, sometimes students freak out because they're like, that's a negative value. Yes, it is, but that's good because remember, this reaction is giving off heat. If we combust something, that gives off heat. So that is okay. Okay. So now I want you to try these next two. Pause me. Okay. Take a look and then come back and I will show you the answers. All right, welcome back. So for the next one, or for practice, I got, this line to keep it separated here. The Q for the calorimeter equal to 70.2. Okay. Now, that's going to be kilojoules. Then that means the Q for the reaction is going to be negative 70.2 kilojoules. Okay. I'm going to change my mass of hexane from grams to moles. And I end up with 0.0180 moles. Okay. I think I've got two problems running into each other. Oh, I think I fixed it. Okay. So then I'm going to take my value divide that by my moles. And I get negative 3.9 times 10 to the third kilojoules per mole. Okay. For the next one, I apologize. There is a problem here. That should be 10 to the third, and I didn't catch that typo until just now. Okay, so here, our Q for the calorimeter is what we're looking for. Okay, we know the E for the reaction in kilojoules per mole. Okay, so we have 1.55 grams of toluene that we combusted. Well, so let's look and see what we know. Okay, the Q of the reaction is equal to the Q of the calorimeter. Okay, well, we know that the reaction was negative 3.91 times 10 to the third kilojoules per mole. So the heat that the calorimeter took in is 3.91 times 10 to the third kilojoules per mole. Okay. Well, from that, we can figure out what that is per gram. Okay. We know that there's 1.55 grams of toluene in the reaction, and there's 92 grams in 1 mole. So we end up with not enough numbers on my paper. Give me 1 second. I'm going to pause this. Oh, I'm not. I'm just going to grab a calculator. Hold on. Sorry about that, folks. I have 0.0168 moles. Okay. So 0.0168 moles. And we know for every 1 mole, we get 3.91 times 10 to the third joules, or kilojoules rather. So that's how many kilojoules we got from the reaction. Okay, so we know that the Q for the reaction is 65875 kilojoules. Okay, well, Q of the reaction is equal to C of the calorimeter times delta T. Okay, plug in what we know. T final. Minus T initial. And we solve for C cal, and we get 4.56 kilojoules per mole. Oh, that's where that should be a decimal right there. That would make more sense. Sorry, somebody has abused my calculator and now I can't see the bottom part of it. That's sad. All right, so that's not per mole, that's per Celsius. And that concludes our bomb calorimeter calculations.